Well, good morning. Some of the pictures, by some reason, I don't know why, but I downloaded less pictures than I got in emails. Maybe it doesn't matter. You can see the pictures on the blackboard. They have no names, and you can see many differences. What makes me personally happy? Many pictures not better than mine, and some are more accurate, some are less accurate, different features, and well, I can't comment on all of the pictures, but this is a very common misconception. Here, magnetic field lines drawn about the coil, but magnetic field lines which we need to analyze have to be generated by magnet at the location of the coil. So the magnet is the source of the magnetic field. Like here, we can clearly see magnetic field lines inside and outside of the magnet. Although this arrow looks strange, magnetic field lines all leave the North Pole and all enter the South Pole, like in this picture. Well, and we have discussed in great details. This is real nice, even red and blue. So we have discussed in great details this classical experiment, Faraday's experiment, although that was not the first experiment which gave him an idea of electromagnetic induction. He perfected later his experiment, and the Lecture law explains kind of what does this minus do. Yeah. So the equations tell us how to sketch the graph, how to calculate the EMF. The Lecture law is less intuitive. So let's just take a look at a couple of experiments related to the Lecture law. You know what? I'm just going to switch. So here, again, it's a classical experiment. We have two loops. One loop has a clear cut in it. Second is continuous, both made of aluminum, so conductive loops. And what's going to happen if we have a magnet and let's say we make it move closer? Nothing. Now we can see interaction. What's happening? Well, at the location of each loop, changing flux induces electric field, but electric field here cannot make electrons travel through the gap, so there is no electric current. But here, in the continuous loop, electric current starts traveling and induces magnetic field, and now we see two interactive magnetic fields, like two magnets interacting. And we, of course, can use our method to figure out what should be happening. So when there is no electric current, no induced EMF. When electric current is induced, it induces magnetic field, and of course, the loop starts moving. How? Well, we can see how if we use our method. So initially, the magnet is far away from a loop. How does it affect the loop? Well, magnetic field lines. Oh, this doesn't do anything. So we need a longer field line like this one. And here we have, at the location of the loop, certain magnetic field. So the flux is not zero, but not strong enough. So if we're moving the magnet closer, what should happen to the flux? Well, stronger field, more lines. So we should have more magnetic field lines at the location of the loop. So what is happening to the flux? The flux increases, well, in magnitude. What is it, positive, negative? We don't know, and we don't care. We didn't set area vector. We don't say, even say words like clockwise, counterclockwise. Yeah. What we say is, because flux increases, the induced magnetic field should point, and now we have to choose between parallel or opposite to the external magnetic field. And if the flux increases, that means the induced magnetic field should be opposite to the external magnetic field. So the induced magnetic field should point, we can say like that, but relative to you, this direction is to the right. If someone would have been looking from behind the screen, that same direction would have been from left to the left. So this is the external magnetic field. This is the induced magnetic field. However, if we remember the very first definition of magnetic field, well, it included magnitude and direction. But according to the definition, this arrow represents a magnet inside which magnetic field line points from south to north. So this is the situation when the magnet is approaching the loop with the north pole facing the loop. What we see is just two magnets. Facing like poles, and they repel each other. And that's what we saw. See? Well, question. If I repeat the same experiment with one difference, instead of making the north pole approaching the loop, I flip it, and I will make the south pole approach the loop. How would that affect the loop now? And of course, since it's physics, we have two options. The option number one, we can draw those pictures, see what's going to happen. Option number two, we can run the experiment, see what happens. We can compare. They have to agree with each other. So you should choose your answer by now. And I'm going to switch to camera again to take a look at the actual experiment. So again, the original experiment with the North Pole approaching the loop. Repulsion, it repels it. The new experiment, what do you expect? I couldn't hear you, but you're right. All right. Still repulsion, of course. When would we observe attraction? Well, why, first of all, why of course? Because it doesn't matter, the flux again increases. When we're moving the magnet closer, the flux increases at the location of the loop, so the induced magnetic field should oppose the change, so still should act like a magnet with the same pole facing this magnet. To make it act like attraction, we should decrease the flux. Something like this. In that case, it wants to go with it. When the flux decreases, the loop is acting like a magnet with the opposite pole closed. So this is kind of cool. Now, just for a second. So the answer, of course, will be repelled. And this is not the question for the Weber sign, but something we can think about. We have here two pendula, one with cuts, second is bulky, a magnet. And what's going to happen? Well, let's just take a look. The idea is simple. Again, if we have a pendulum with many, many cuts, it's like a ring with a cut in it. We cannot induce at least any strong current. If we cannot induce current, it doesn't matter if it's made of aluminum or wood or anything else, plastic. So it should not be affected. But this one, why do I use a camera if I have it somewhere else? But this one, bulky one, should have electric current induced in it. And how would that affect the motion of this pendulum? Well, let's see. So the first one just keeps swinging. Friction makes it stop. This one practically doesn't move. It could get through. Now, those electric currents have a name. Electric current induced in a bulk material has a name, eddy current. And we can see that eddy current stops it. What would happen if instead of a minus in a Faraday's law, we would have a plus? In that case, in the Lenz's law, we would have to switch one word from oppose to increase. And in that case, even little swing would make it swing even larger, even larger. It would amplify, and that can happen. That would violate the law of conservation of energy. So that's what minus does, and that's what the word opposite means. It only can slow down the changes. It cannot speed them up, amplify those changes. And this phenomenon actually practically is being used in brakes. Electromotive has wheels made of iron or some alloy. So if we bring electromagnet close to it, we can induce strong eddy current in it, and that will make it stop. And we don't have to use actual physical contact, so it will make it last longer. Now, gentlemen in the first row, you've been helping me before, so could you please tell me what do you feel if you move by one hand this wooden piece and by another hand this? I'll have to be more specific. Which brings you, gives you more resistance?
The metal one.
Well, that's not a metal.
Oh.
That's a very, very strong magnet. And I actually, well, thank you. So you did that, but everybody else can do the same just before leaving the room, you know. So you can feel, you physically can feel how resistive the motion is. Nothing with the wood. And, well, what's going to happen if I let it go? That's it. What's going to happen if I let this go? Slowly, because when it's moving, it induces in this huge, heavy copper plate a very strong eddy current, which slows any motion we try to make with it. That's what resistance is. And a similar experiment you have done or will be doing in the lab if you have a tube like that. You take a piece of chalk. What's going to happen? Well, first of all, what's going to happen? It falls. So you have to be really quick to catch it. Years of practice. What's going to happen now? Slows down. Change a minus to a plus. That would have been like a shooting device. You would just put it in and that would shoot it out. But where would it get the energy? Energy cannot be created from nothing. So that would violate the law of conservation of energy. That's why the Lenz's law says to oppose the change, and that's why the Faraday's law has a minus in it. Well, that's a review, and we saw this slide before. We just didn't do any example, so let's do one more example, just one example. So what we see here, oops, I missed this number. That's not 2. That's should be 3 now, right? Okay, so everything changes. So this is just an enlarged picture of the graphs. And we use the analogy between position and velocity here to analyze relationship between flux and EMF. If this is the graph of the flux, the slope times -1 gives the graph of the EMF. How do we make it? How do we make transition backwards? Well, we do it using area. So if on the graph for the EMF, we can measure or calculate certain area, that area will be equal to the difference between the flux at the initial and final locations or times. And here, the question is about the slope of the flux at t equals 3. Where is t equals 3? T equals 3 is here between 0 and 5. That's t equals 3. And if we look at this, time, EMF is positive. Well, we actually can calculate it because it's a straight line. So the graph for this function is linear, some kind of a slope times time plus y-intercept, and y-intercept should be equal to 0, and we can calculate the slope, which is what, 10 over 5, 2. So we don't need to do that, hence. This is just an example when it could be done, when the function is simple, which means actually the flux should be quadratic. It's like going back from linear equation for velocity to the original equation for position. But we don't need the equation. this is basically about, do we know that the minus is a part of the equation? Because this is the relationship, which means if you need to calculate slope, that should be -1 times EMF. If EMF is positive, the slope will be negative. Now, before I move on to the example, one more, actually, from a practical point of view, much more important representation of the Lenz's law. Not sure if it's going to help, but I'll try. That's the camera. No, I want it in the dark. I break everything. Okay, dark. Camera. Yeah. Okay. Not sure, actually, if it's better to look at this or that, but so what I have here is a battery and two bulbs connected how? How do we call this? Parallel, connected in parallel. When I close the switch, they both bright. Open, dark, close. Now what I want to do, I have a very, very strong inductor. It's just a huge coil with many, many turns. And I want to insert this in a circuit with one bulb, the top one. So all I have to do is just break the circuit. I want to connect this in series with this bulb. And we still have to remember what does it mean connected in parallel, connected in series. Now let's see what's happening. What's happening? Did you see the difference? Any difference? Time delay. This now gets brighter a little bit later. Why? Because as soon as we close the switch, electric current starts traveling through this coil, but that induces magnetic field inside this coil, but that induces electric current, which opposes the change happening to the original electric current. How opposes? Slows it down. So that's why this bulb takes longer time. Theoretically, well, it's hard to see, but we should use a capacitor. But theoretically, if I open the switch, also this immediately gets dark, and this should a little bit after, but it's really difficult to see. Well, actually, see? And you don't have in your cell phone or computer a coil like this, but you have many, many, many tiny coils which do exactly the same job. They manipulate with electric current, slow it down in a certain way. Plus, if you add a capacitor, you actually can generate electric current with a precise frequency you may need for whatever purpose. This would have been so-called RC, R resistance, C capacitor L, inductor RCL circuit, which has been used initially to make the first radio. We will talk about it later. All right. Done with this. Back to calculations. Now we need to calculate, of course, as an example, by some reason, some symbols disappear. Well, I use the PowerPoint on Mac, and Mac and Windows hate each other, so. All we have to do is just calculate the area. Right now, this is much less physical problem than geometrical. We know from the analogy between xv and phi epsilon that the area of this graph should be equal to difference in flux, and the initial is set to 0. So if we want to calculate the final, it's going to be equal to negative 1 times area. And how do we calculate area? Well, we can break it in 2 triangles, or we can see the symmetry, and the symmetry here says the area of these 2 triangles is equal to the area of this one rectangle. So negative 1 times 5 times 10, negative 50 watt, WB Weber. And as we have mentioned, the graph for the flux should be quadratic. Yeah. So how does it look like? Well, at first the slope should be negative because EMF is positive, and okay, up to this point, up to 5 seconds, and then the slope should become positive. So this is negative, so positive. How do I draw it? The initial was 0. I know I have to end at negative 50. Well, actually, probably should go this way. Something like this. We can write an equation, and quadratic equation, and then plug numbers in and calculate. Now, the couple of more slides on practical applications. First, generators. A generator, as we know, is a combination of a permanent or electromagnet and a coil which rotates, so like this one, and it generates electricity. We know why, because when it spins in magnetic field, the flux through each individual loop changes. That should induce electric current. What's going to happen if we attach a second generator? It's actually acting like a motor. There is a symmetry, because the motor and a generator have exactly the same things inside, exactly the same structure. So technically, they're replaceable. It's a matter of how we use it. Yeah. If we want to transfer mechanical energy, my hand does mechanical work into electrical energy, that's a generator. But if electrical energy, get it transferred into, well, optical, light, heat, or into mechanical, that's a motor or engine. And to describe it mathematically, of course, we have to start from the Faraday's law. And we need to go back in time, PY105 rotational motion. So let's say we have a loop and a magnetic field. When it spins, the angle between magnetic field and the area vector of the loop, which we can set to any direction, changes. That's what's important. This angle, theta, changes. How? Now, PY105 says if the rotation happening with constant angular velocity, the angle changes linearly, constant velocity equation. So the flux will change, but not linearly. It will change as a cosine or sine, yeah, because we can always switch from cosine to sine and back and forth if we choose this constant correctly. This is just a constant. Very often we can set it to 0. So how does flux change? Well, in general, something like this. That's how a graph of a cosine as a function of time looks like. That's it. And if the flux changes, it must induce EMF according to the Faraday's law. So because this is, well, a true analogy of a simple harmonic motion, we know everything about this type of the motion by transition, by analogy. For example, the amplitude, the maximum value of EMF will be related to the maximum value of EMF induced in one loop, which is, we can say, the speed of the flux. Yeah? We always can imagine flux 5 represents x coordinates, so EMF represents velocity times -1. And just replace all the letters from simple harmonic motion equations with the new letters. That's it. And if we have several loops, we just have to multiply by the number of loops. That will be the maximum EMF. And of course, as before, we had a couple of special cases. Special case number 1. Let's say initially magnetic field is perpendicular to the loop. What does it mean? That's T equals 0. That means initial flux has maximum value, which is just A times B. And well, depending on how we choose the area vector, depending on how it spins clockwise, counterclockwise, we can sketch a graph which should start from maximum value, which could be positive or negative, but again, for the sake of simplicity, positive. And how would the graph for EMF as a function of time look like? Well, first we have to, again, take a look at the slope. Bless you. So it starts from 0. There is no slope here. Then the slope is negative and reaches maximum. It's not, again, 0. Now, that's not EMF yet. EMF is -1 times the slope. So we have to flip the graph. And what we can see, for example, when the flux reaches maximum value, at this instant, EMF is 0. Or if we are calculating electric current, the graph for electric current will have exactly the same shape as the graph for EMF. A second special case, all right, let's designate some area for that. When, let's say, magnetic field points like this, but the loop is initially parallel to magnetic field lines. What does it mean? It means that now, at t equals 0, the initial flux is 0. There is no flux. So how do we sketch the graph now? Well, technically, with this information, we have two options. We start from 0 and go up, or we start from 0 and go down. And that depends on the direction of the rotation, for example, and the choice of the area vector. For example, well, we need to set the direction of the area vector. Please tell me left or right. That's the loop. We can choose area vector to the left or to the right. Choose it. Thank you. Now someone has to tell us how does it spin, clockwise or counterclockwise? Anybody? I'm asking you, how do you want it to make? So you want to make it to spin counterclockwise. Okay. In that situation, in a fraction of a second, so we have to imagine what's going to happen. The loop turns by a certain angle. So magnetic field still has the same direction, but now the area vector is not perpendicular to it anymore. That's the area vector. Now we can take a look. There is a flux now, and that flux now is positive. With a different choice of rotation or with a different choice of area vector, that flux would have been negative. But in this experiment, with this choice of area vector, with this choice of rotation, the next flux is positive. So starting from 0, the graph should go to a positive number. And now we know it's going to go up to maximum, back to 0, to another maximum, to 0 again. This is how the graph for the flux as a function of time looks like for this particular situation. And now, again, the slope. What is happening to the slope? The slope actually is not 0 now. Here, the slope is a positive, some positive number. But eventually, it becomes 0 when the line becomes, tangent line becomes horizontal. So how would the graph look like? Well, like this. But that's the slope. EMF is -1 times slope. So what do we have to do? We have to flip the graph. And these are only important situations, critical situations, when the flux begins from 0 or when the flux begins from maximum value. And we can see again that when the flux reaches maximum, there is no EMF, meaning no electric current. Instantaneous value is 0. It is not 0 before or after, but instantly, at this instant, t, which is a quarter of a period, by the way, if you remember, the current becomes equal to 0. So this is all based on our knowledge of graphs from simple harmonic motion. We just use different letters. What is a period, by the way? One period is, yes. Exactly. So this is exactly one period. And when the flux changes, EMF changes, electric current changes, they all have the same period. Now, so extreme situations, extreme cases, and the reminder from PY105, this is how we related position and velocity as a function of time. This is one specific case, yeah, when the motion starts from the maximum displacement from equilibrium. It's an equivalent of the rotation starts from maximum flux. And this is the amplitude, which we proved. So now we just replace the letters, again, get the same expression for the amplitude of EMF with one difference. We need to multiply by the number of loops. And these are graphs. And we mentioned once or twice this term, root mean square value. We used it to describe not average, but some kind of a constant number which we could use to represent the alternating variable. In this situation, alternating current or alternating voltage. So if we want to use, for example, the Ohm's law, which relates EMF, current, and resistance, on one hand, we could use it for any instant, but on another hand, we can use root mean square values for each. That's just easier. That's not a question number 4 anymore. Now, what number is now? 5? Still 4? Oh, I'm good. I made 2 mistakes. Sometimes when someone makes 2 mistakes, they cancel each other out. That's it. So, for the graph on the left, when do you think the EMF would reach its second maximum? So you can look at the graphs in your notes, or you can sketch a graph again to oops, what's happening? Something is happening. My pen doesn't work anymore. Okay. Okay. You do your part. I'm going to do my part. Seems working again. Don't breathe. So, what is happening to the slope? 0, positive, reaches maximum positive value, decreases, and becomes 0 again. So the slope, I'm drawing EMF. The slope is 0, EMF starts from 0. And if the slope is positive, EMF has to be negative. Negative. It should reach maximum when the flux is 0. Then it should go back to 0 when the flux is at the second maximum. That's the graph. The maximum again, 0. That's the maximum number 1. And this is what we call, how do we call this? Amplitude. This is the amplitude EMF again, maximum value of EMF. So this is the instant when the second maximum is reached, and that is 6. Just graphing exercise. Specific problem, generator. A generator, okay, has a core made of a coil which has 50 turns. And each loop, it's actually a square loop, not circular. Okay, so the area of each loop will be equal to 0.03 times 0.03 meters squared. And the coil spins at angular velocity 500 rotation per minute. What is wrong with this? Angular velocity, as anything else, has to be measured in radians per second, well, using the international system of units. So we have to convert it into radians per second. So revolution per minute. First of all, a minute, 60 seconds. And revolution. One whole revolution equals 360 degrees, but we cannot use degrees. So what? 2 pi radians. That will be radians per second. Now, times. The coil is a uniform magnetic field with a strength of 2 Tesla. The initial orientation of the coil is such that initial current has maximum. So current at t equals 0 equals maximum. What does it mean? It tells us how they should, the orientation between the magnetic field and the coils. When the current reaches maximum, the flux has to be 0. That's what it means. And the flux is 0 means magnetic field is parallel to the coils initially. That's what it means. So the flux starts, the initial flux is 0. Well, that means the EMF should be represented by an equation which has, well, amplitude times a certain function. What function? Sine or cosine of what? Well, angular velocity times time. It also could have been plus or minus, but in this situation, there is no information about that. We would have to know what is happening, not just at t equals 0, but in a fraction of a second to figure out if it goes in the region of positive flux or negative flux. So it doesn't matter. We have to choose between sine and cosine. That matters. Well, the flux starts from 0, which means the flux should be represented by sine, which means EMF cannot be represented by the same function, which leaves the cosine. And we can calculate the magnitude, the amplitude, and that's it. Just plug in numbers in now. So we can make an assumption that the graph for EMF looks like this, starts from positive EMF. We actually have a different, no, we have extra information. I forgot about this. It should start from a negative maximum. My graph starts from positive maximum, which means I have to cross out the plus. I have to write wrong and change it to the opposite. So it should start from a negative value, negative maximum, goes like this. So the equation will be equal to -1 times maximum value or amplitude times cosine of omega t. Now we can check the graph for the flux. The flux begins from 0, and in a fraction of a second, EMF is negative, which makes the slope of the flux is positive. So yes, that was the right way. So, or these were two choices, positive slope or negative slope, and now this point tells us it should be a positive slope, so that should be the graph for the flux. Okay. So we just, again, again, solving a problem in physics like knitting, putting together loops. Well, and now the last practical application, transformers. A transformer is a device which has two coils connected by a core. So they share the magnetic flux traveling inside the core. And how can we use it? Well, we can use transformers to change the values of electric current or voltage EMF or EMF induced. Here, so I have a function generator. I don't want to use the power outlet for alternating voltage. Is it on? No, it's not on. And this device will measure voltage, but it has to measure alternating. Okay, and same this one. So I have to switch from DC to AC. Now, of course, nothing is happening. Nothing is connected to anything. First, I have to connect, well, this is a generator to a transformer. I can connect it twofold. This could be connected to the generator or that. What difference does it make? Well, these coils have different number of turns. This one has 400. How do I know? I can read. This one has 800, twice more. And if I connect this coil to the generator, I expect that here my voltage will be twice higher. And in this situation, we call this transformer a step-up transformer. I could switch it, and that would have been step-down transformer. The same device, but used differently. So, connecting. Now I need to measure, actually, what I want to do. This is 100. I want to make it 60, like standard power outlet. 60, 50, different countries, different standards. So 40, 70, 66, 65, something like that. It doesn't matter. So now I have to connect. Well, again, I'm connecting in parallel, so it doesn't matter how I do it. I can connect it here or there, and I have to see 7 volts. Okay. Now I have to measure the voltage across the secondary coil. So I have to connect this coil to the second multimeter. We would expect 14, but in reality it's never exactly the same because of the loss of energy. There's some friction, well, resistance, plus magnetic field also is not completely inside this core. If I measure magnetic field outside, it's not going to be 0, so there's some magnetic field lines which don't go through the secondary coil. But it's close enough, yeah. 7 times 2, 14, 12, more or less, yeah. Good. And now let's make it step down. What do you expect to read here? Well, it's the same generator, so it should be same number. But now, because I go from 800 to 400 turns, I should read, well, 7 divided by 2, 3.5. But there's additional loss, 2.8. That's how a transformer works. And the easy solution is just break everything down. How do we use transformers? Well, first of all, again, in every device we have them. If we need to go from 120 volts to 12 volts, we have to use a step-down transformer. And an ideal transformer where there is no loss of any energy, the total amount of energy which supplied to the primary coil should go to the secondary coil. And the Faraday's law and the law of conservation of energy gives us two mathematical relationships. Number one, in each single loop, the flux is the same. So more loops, more flux, less flux. This ratio, the voltage in a coil divided by the number of coils, represents EMF induced in a single loop, should be the same for both. That gives a relationship between voltage and number of turns. However, because, well, in an ideal transformer, energy supplied per second, which is power, is the same. How do we calculate power? Voltage times current. This product for both coils should be the same. So this also gives the relationship between electric current and the number of turns. And we can see that if we increase the number of turns, we increase voltage, but we decrease current. We cannot increase both, because that would mean we gaining energy from nothing. The total amount of energy remains. If we decrease current, we increase voltage. If we increase current, we decrease, what did I say? Increase current, decrease voltage. Decrease current, increase voltage. And when we need to produce electric current, we use power plants. They produce very high voltage, potential difference, very high voltage EMF. But it's not high enough to transfer, because as we know, the energy loss depends on electric current, I squared times R. So we want to decrease the current, we want to increase the voltage as high as possible, and then make it travel through wires to decrease the loss of energy. So we have to use powerful step-up transformers, but then when we get in closer and closer to towns, cities, we use a set of step-down transformers. Eventually it goes on average, root mean square value, to 120 volts we have in our power outlets. So this is how it's been transmitted. If you know the history, Edison was a proponent of direct current, but Tesla was a proponent of alternating current, and alternating current is much easier to transport, to transmit, because we can use transformers. We cannot use transformers for direct current. Although this actually was the original experiment of the Michael Faraday. This is what he did. He had a coil, number one. He had a coil number two connected to a multimeter. And he used a battery to induce magnetic field in one coil, and he was watching at what was happening in the second coil, well, using the multimeter. And then he perfected his experiments, started using permanent magnets. So what's going to happen? Well, there are several options here. Number one is definitely wrong, because there has to be some induced electric current. But if right here, instead of a resistor, we would be using a galvanometer, what would it show? Would it show constant electric current, another constant, or some kind of a brief jump, and then 0 again. And well, you have to answer this question, and we have an ability to answer this question using the Faraday's law. What's going to happen with magnetic flux when we close the switch? When the switch is closed, the electric current starts traveling in the primary coil. Well, because of the Lenz's law, this electric current, number one, reaches a certain value, not instantly. It takes, well, a fraction of a second, but it takes some time to reach that value. As we saw in the experiment with 2 bulbs. So, magnetic field, which this current generates, and hence magnetic flux, change in time from 0 to a certain final value. After that, it stops changing. But now the same magnetic flux, because of the iron core, will be traveling through the secondary coil. So it's not just phi 1, it is also phi 2. So we could sketch the same graph for the flux through the secondary coil. And now, what should happen to the EMF? Well, it should be nothing. The most important part of our analysis is related to this part. Here, the flux number 2, after a certain time, remains constant. Means does not change. Means EMF supposed to be 0 again. So, well, for the magnitude, it should be negative, but for the magnitude, we should see something like this. A brief current, which goes back to 0 again. Well, let's see. The battery. Do you see anything? Was Michael Faraday wrong? No. He just needed a core. That's how he did it. He actually had windings, turns of both coils put together. So, what's going to happen now? Now we can see. So, when I touch the battery, actually I can just plug it in. Oops. When I plug it in, it induces magnetic field. That magnetic field induces electric current here, but after a while, nothing. So it briefly goes to maximum, and when magnetic flux doesn't change anymore, it's 0. How can I change it? Well, let's see. I can move the core. When I move in core, it's like moving the magnet. Again, that changes the flux, and the flux, changing flux induces EMF. Well, now, too many experiments. Now we have to talk about a little bit about magnetic properties of materials in general. So this is a permanent magnet, very strong. If by mistake I would had it attached to something else, it's actually really hard to take them apart. And magnets, of course, not the only materials we know. What does make a magnet a magnet? So if we could look inside, we would see actually many, many, many tiny magnets, but not actual smaller magnets. No. The thing is that everything is made of atoms. Atoms have electrons. Those electrons have charge. So when they spin about the nucleus, they represent electric current, and that electric current generates magnetic field. Plus, every electron has a special property, a spin, which is like analogous to a ball spinning about some axis. So this spin moment is responsible also for generating magnetic field. So every material, wood, iron, platinum, anything else, has a lot of electric current inside, tiny. And in general, they might point in all directions chaotically. But in a permanent magnet, they actually aligned in specific direction. Here, net field is 0. Here, net field is not 0. And if we apply an external magnetic field, we make those tiny magnets aligning more and more. That's how core acts. It amplifies external magnetic field. In an ideal magnet, all spins and all currents generate magnetic field, which point exactly in the same direction. And this piece doesn't look like an iron. It's a crystal, but you can see it's being attracted, but it's a very weak attraction. So we call it not a ferromagnetic like an iron, a paramagnetic. But some materials actually might be repelled. They experience repulsion. For example, a simple graphite, which everybody has in a pencil. So this is like a huge pencil core. The hardest part to keep it not broken from people playing with this. So a magnet, and you see I don't touch it, but it's being repelled by the magnet. So these materials have name diamagnetics, diamagnetism. Magnetic field doesn't want to stay inside, it wants to get out. And an ideal diamagnetic has been discovered many years ago, but in 1986, an ideal diamagnetic which can be used at relatively high temperatures has been discovered. This is a high temperature superconductor. Superconductor means when temperature drops below a certain level, it has no resistivity at all. But if electric current can travel infinitely long, that means it can act with the magnet infinitely long. All you have to do is just cool it down. To cool it down, actually, to cool it down, I need to use a very cold liquid. And I have it. Liquid nitrogen. Oops, oops, oops. Come on, come on, come on, come on. So a magnet sitting, well, this is the backup, sitting on the, well, on a superconductor. I need liquid nitrogen. I have it. in a dewar. But first I have to pour it in a smaller dewar, and then from a smaller dewar in an even smaller dewar, and then from a smaller dewar even smaller dewar. Well, that's enough. I think I moved the camera. Now we can use this. Now we wait. While we wait, what's going to happen if instead of cooling down, we're going to heat it up? Oops. Where is it? Where is it? Here. Too much fog. Well, this is the magnet. I can touch it, and you can see it spins. That only can happen if it floats. If it floats above it. It doesn't touch this black piece anymore. Well, this is high temperature superconductor. They now are actually relatively cheap for this experiment. So what is happening? Well, this superconductor keeps this magnet. This magnet cannot fall on it. Why? It induces electric current, which induces magnetic field, which keeps it floating forever. Well, if I keep adding liquid nitrogen. Unfortunately, this material cannot be used like a wire. It's very fragile. So far, to make something more than this is very expensive. But hopefully we'll figure it out in the future how to make wires from superconductors, high temperature superconductors. Low temperature superconductors like copper, of course, also can be used, but they would require liquid helium instead of liquid nitrogen. Liquid helium is much more expensive. Liquid nitrogen costs like milk. All right. Ooh. So what's going to happen now if instead of cooling down objects, I will heat them up? This is a magnet. I don't know if you need the camera. Maybe not. And, well, this is a standard nail. See? It's attracted to the magnet. What force does attract it? Gravity? No. Love? No. Hate? No. Hate can attract. All right, the hardest part is to find the location of this magnet where the nail is barely attracted to it. You know, like in life, barely attracted, but okay. All right, so I'm moving magnet higher and higher, watching. All right, let's hope it's gonna be enough. Now I want to heat it up. And this is how you kill attraction. So what happened? We know that when temperature increases, more and more chaotic motion happening inside, that's it. So all those internal magnets, which were more or less aligned with the magnetic field of the magnet, due to chaotic temperature motion, have been becoming less and less parallel, less and less aligned, and eventually they couldn't support the nail. They could not work against force of gravity anymore. That's it. And that completes everything we learn about magnetism. And now we start a new topic, waves. I'm going to do it tomorrow. There are simulations. You can play with them already if you like. Simulations which help us to visualize what is happening inside a wave. First of all, what is a wave? Well, you have to imagine a rope attached to a doorknob. You hold one end, you wave that end, and a pulse starts traveling away from your hand. Like this. So we can imagine this is an infinitely long rope or string or spring, and you make a wave, make a pulse, and it travels away. Does the rope move? No, the rope does not move. A wave cannot transfer any matter, any medium, but it transfers energy. If I had, instead of a window, a wall, that pulse would push on the wall. Well, instead of something like this. And the wall would push back, and the pulse would be reflected. That's how waves are reflected of different surfaces. And to describe a behavior of a wave, we just need to describe a behavior of a single pulse, because a wave is just a combination of pulses, one after another, one after another. This wave has internal friction. You can see that next pulse has a lower magnitude than previous, and it's called damping. We can set it to 0. That's the only case we're going to consider. An ideal, no friction. Oops, what's happening? Yeah. An ideal rope, and there are different types of waves. We're going to talk about mechanical waves first. That includes waves on a string, spring, sound waves, also mechanical waves. And later we're going to talk about electromagnetic waves, including light. There are two types of waves, transversal and longitudinal. In my applet, you saw that I was moving the rope up and down, and pulses were traveling horizontally. So each particle on a wave was moving perpendicularly to the direction in which wave as a whole was moving. That's a transverse wave. A wave, including sound wave, when motion of each particle happening in the direction in which wave propagates, that's what we call longitudinal waves. I'll show you tomorrow examples. This is not a question. We have no time. This is just an example of a difference between a transverse wave and a longitudinal. If you have a slinky at home, you can play with this. If you move it up and down, and the pulses propagate horizontally, so this arrow represents the velocity of a wave but for each individual wave particle, the velocity is vertical. So these two directions perpendicular. Here, we push or pull on a slinky, so each individual wave particle travels horizontally, but the wave as a whole, all pulses also travel horizontally. So the velocity of each particle and the velocity of a wave as a whole, parallel or anti-parallel. In this case, we call it longitudinal. Of course, to describe a wave, we have to introduce certain physical quantities. First of all, we start from a period. There is a source. It could have been my hand moving the end of a rope. That source is responsible for making all particles move up and down with exactly the same period. The period of a wave is always equal to the period of a source. And then pulses travel away. If we take a photograph of a snapshot of a simple wave, it would look like this. That's a photograph. We can see different particles at this very instant displaced differently from the equilibrium. And each particle in time, as you saw, oscillates up and down, up and down. This particle oscillates up and down, up and down. This particle oscillates up and down. And the whole picture also moves to the right in time. But they never go away from equilibrium larger than this distance. So that's why we call this the amplitude of a wave, the maximum displacement from equilibrium for all particles. And we can see that along a wave, there are particles which move up and down simultaneously, in synchrony. We call it in phase, like these two. They displaced from equilibrium at the same time at equal displacement. The distance, the shortest distance between two particles like that has a name, a wavelength. So this is one wavelength. How many quarters every period has? 4. How many quarters does every wavelength have? 4. 1 quarter, second, third, fourth. 4 quarters. So we don't need to see the whole wave to figure out the wavelength. At the minimum, we only need a quarter of it, and then we can multiply by 4. Now, just one more time. Well, we can slow it down a little. So, a model of a wave, snapshot, a photograph. Where is the wavelength? Well, from one maximum displacement from equilibrium to another maximum displacement from equilibrium. It does look like it travels as a whole to the right. In a fraction of a second, I'll try. Oh, it works. So this is the snapshot of this wave right here, right now. If we wait a fraction of a second, this is how it looks like now. This is the next profile of the same wave. So we can see it looks like it just moved as a whole to the right. How do we describe the motion? Velocity. Velocity equals distance traveled over time. But if we look at how a wave travels, it takes exactly one period to travel exactly one wavelength. So this is how we can calculate the speed the wave speed, the speed wave travels, wavelength over a period. And if we remember from the past, from PY105, the frequency is equal to 1 over a period. Hence, if we combine these equations, this is how usually people write the relationship between speed, wavelength, and frequency for a wave. I want to save it for the history. So these are the equations. And again, a lot of the information we can base our analysis of the wave motion comes from PY105 of analysis of a simple harmonic motion, because each individual wave particle makes simple harmonic motion. They all make simple harmonic motion with the same period, with the same maximum speed. This is not a speed of a wave. These particles travel up and down. When they reach maximum displacement, they stop instantaneously, then come back, speeding up faster and faster. And here, when they travel through equilibrium, they travel at the maximum speed, and then they slow down again. And from PY105, we know how to calculate that maximum speed, angular frequency times amplitude. So what do we know about simple harmonic motion? Everything, including equations. So now we just have to, this is just a copy from PY105. So refresh it. And now we just have to use that knowledge to derive an equation for a wave. An equation for a wave equation should describe displacement from equilibrium at any time, at any place of any wave particle. And to do that, we look at a single pulse. And we know that if we wait a certain time, the same pulse, which reaches a new location, still keeps the same profile, the same shape. It doesn't decrease, no friction, an ideal rope. So the displacement here and now is equal to displacement at the origin these seconds before. That's what it means. Now we just have to write that mathematically. How do we write it? This is how we write it. The displacement here and now is equal to displacement at the origin this time before. That's a wave equation. Thank you. I'm going to just move it. Oh, you go ahead.